Okay, so the easiest one that you can see if you are given a convex function, so the easiest one that you can say is that for any point here, we know that what is the gradient here. Let's say that this is the gradient. So what we can do is that we can just go downhill negative direction of the gradient. Okay, so these are the easiest things that you can show, and then it can converge easily, right? The question is how fast it can converge, but then there is no question about the convergence. So this is the meaning of this guy. So the next iteration is you will initialize that with some point. We are not talking about the initialization anyway, but with some x you will initialize and then update x by x plus some alpha k, which is called a step size, non-negative values, minus gradient of f. So this is, let's say, minus of gradient of f. This is a descent direction that reduces the objective at every iteration. And that can converge very easy. And then you have these two forms of convergence. But actually, there are lots of other variations of these forms. But then if the function is convex and L is smooth, so again, it means that it can be lower bounded by an affine function and upper bounded by a quadratic function with curvature L. For a step size, constant a step size is smaller than 1 over L, you can have these convergence rate. So what does it mean? It means that if you go with every iteration, you will reduce the object. So this is the x0 minus x star, norm 2 of that. So this is the difference between the initial point and the distance between the initial point and the optimal solution. So you're going to reduce that in every iteration. And then by what factor? 1 over k, so as to speak, in general. Something in that order. Are you happy with this rate? Well, who can say? Well, it depends on the application, but usually this is not fast at all. This rate of convergence is not fast. Do you have a question?
Is there a proof that we cannot do better than this?
Yes. Actually, here we are doing much better than that in this case. And then there is a proof that what is the fastest approach that we can do, which is called acceleration method and Nesterov proof. We will go to that. You can find the in appendix of this slide. Probably I don't have time to go through that, but then the main proof sketch is there, so you can just follow them. How you can prove that, okay? But the main idea is that how many iterations you need for a smooth and convex function. You're gonna need iteration of the order of 1 over epsilon for epsilon optimality. Epsilon optimality means that this guy is smaller than some epsilon, okay? So for any epsilon, you're gonna need this amount of iterations, which is not good usually. Okay, what would happen now if we add a strong convexity? So if the function is mu is strongly convex, and if it just happens that for some technical reasons, alpha is smaller than this, then you can show that the so-called linear convergence rate. So let's start with x. So with every iteration, don't worry about these two. Just put these two inside that guy here. So you can say that xk plus 1 minus xk, norm 2 of this guy. Let's put it here. Oh, no. Put it here. Norm 2 of this guy is smaller than some c to power k, for some constant to power k, b, where b, let's say, is the distance of the initial guess. So the distance of your initial guess with respect to the optimal solution, okay? Usually we do have a bound on that because we are saying that x comes from this set, so there is a boundary on that set. How far you can be within that set with respect to the optimal solution. This is b. So this is the meaning of linear convergence rate. So essentially it says that at every iteration, so the meaning of that is like this: xk plus 1 minus x star. Actually, that should be x star. So x minus x star is less than c xk minus x star. So well, you should have norm 2 here anyway. But then the thing is that at every iteration, you linearly reduce or be closer to the optimal solution. So this is the definition of linear convergence rate, so-called. So if you do have this regime, then the number of iteration gonna reduce to log of 1 over epsilon, which is much, much better than convex. But one question, what would happen if you're given a function and let's say this upper bound here for some k is, I don't know, 10,000. Let's say this number of iteration for some epsilon is 1 million. And then you will see the convergence after 1,000 iteration or even after 100 iteration. Is there anything wrong? So the bound says that we need to have this for million for epsilon optimality, but in practice you will see after 100 iteration you have that epsilon optimality. So what's wrong here? No, there is nothing wrong. It's just theoretical bound. It's very conservative, extremely actually conservative. But then this is what we can do. So don't be scared if these, of course having these bounds are quite great, but then don't be scared if this says that the number of iteration is just too much. Don't worry. Usually they would work in practice. Not all of them, of course. But then it's good to understand the reason. So this is on x, and then you can show the objective function would decay, something like that. Some food for thought. I'm not going through this slide, but then this is something that I didn't have time to cover here. I would imagine that. So put it here. So just think about these three questions and just check this one. This is a very, very nice website where you can play with the parameters. There are lots of codes there where you can play with different parameters of gradient descent, many, many different versions of that, and then see convergence rates, okay? Very, very nice to understand how this gradient descent works. But then these are three questions, not mandatory, of course, nothing like homework, but then good to know. So this one, for instance, is the projected one, the thing that we have discussed. So just imagine that instead of minimizing, let me see. Okay, so just imagine that this one, so here I didn't mention. So here, this gradient descent will minimize a function of f of x over some x belonging to, no limitation on x actually, so belongs to Rd in general. But then what would happen if x is constrained to be within that convex set? So we are not allowed to pick as the optimal solution any x, but something within that set. Then you can add, so this is what is asked, so then you can add this step, which is essentially what we have seen the first part. So just add that to the steps after the update, just add that. And then you can, so essentially modify the solution, and then you can solve this new optimization problem, constraint optimization problem. Then you can call it projected gradient algorithm. And then you can go to all the steps of the proof and then see that there is nothing will be changed in terms of convergence rate. So same convergence rate, absolutely. To do that, you will use something called contractivity of this operation. Anyway, just think about all of them. So this is the function that I have mentioned in the first part. This is called conjugate function. Pretty useful in many, many things. So for some functions, for instance, it's real hard to know what is the objective optimization on the actual function, but there is a way that for that class of functions, the conjugate functions are known. So it's much better to work with the conjugate function for those class of functions, for instance. But then one thing is pretty interesting, that if the function itself is smooth and strongly convex, then the conjugate function is smooth and strongly convex with these parameters. It's pretty interesting. Okay. Try to think about them, and if you can, even prove them. Okay. So, gradient descent for strongly convex functions and smooth functions, actually. So, just give one example here. So, just look at this guy. So, at every iteration, the solution gonna be closer to the optimal solution at this rate. So, this is the linear rate that we're gonna converge. Okay. And are we happy with this rate? I mean, theoretically. So two things can happen. If L is very close to mu, let's say L grows to infinity for some constant mu, then at every iteration, we are not actually improving anything at all, right? It's because we will be closer to the optimal solution by a factor of 1 minus this guy, and then this guy will go to 0 anyway. So we are not converging. So what does it, well, we are converging, but then the thing is that we are not fastly converging. So what does it mean? Geometrically speaking, it's like this. So when L divided by mu, which is called by the way condition number of this function, if the condition number is really large, then what would happen is that by the definition of the gradient, you have to go to the negative direction of the gradients, okay? And then what would happen is that at this point, the gradient is here, so the negative direction is here. At this point, the gradient is here, then the negative direction is here. So you will do these form of isolations, okay? Oscillations. Then what would happen if L divided by mu is so large? So this is actually, I guess, that L divided by mu in order of 10 or 20 or something in that order. What would happen if that is million? Then essentially you're optimizing something like this. These are sub-level sets of the function. So then you're optimizing over something like that. Then the optimal solution is the iteration of the gradient descent would be something like that. Extremely poor. But what would happen if L divided by mu is just a small? And then by definition, L divided by mu is lower bounded by 1, right? Because L should be greater than mu anyway. So if it is 1, then we have a perfect circle. So everything is round in all directions. Then in that case, gradient descent works just fine. So if you have gradient descent implemented and then it works just fine with 100 iterations, then that's okay, you're lucky, that's it. Because in most scenarios, especially in high dimension, this is not the landscape of the optimization. This is actually the landscape of the optimization. So gradient descent is not the best things to do. It's very cheap in every iteration, but that is the main problem. You may need a lot of iterations to converge. What you can imagine is that this is the landscape. Is there any operation that we can change this landscape to make it a bit more to that and then run the gradient descent on that? Yes, it's very easy. You can do that. This is called preconditioning. And this is actually the main idea of descent methods, in particular steepest descent. So what is descent method? Descent method, it says instead of gradient descent algorithm, which this is gradient descent, xk plus 1, xk plus alpha k minus gradient of f at xk. Okay? It says instead of going toward the negative direction of the gradient, go toward some descent direction. And then the only limitation on the descent direction is that that descent direction should be chosen to have to somehow reduce the objective function at this new point. Okay, so this is the only limitation that you need to have for the definition of this descent direction. But then you can easily see that this implies that we should be in the same half space as minus gradient. So what does it mean? It means that if this is the gradient, so this is the half space of minus, this is the minus of gradient at this point. So this descent direction should be somewhere here. So either this one, or even this one. So whatever the vector within this half space is just fine, okay? And they will satisfy this constraint. So this is the only limitation that you need to have. A steepest descent says that among all potential vectors that you can choose here, pick the best one. So this is the definition of a steepest descent. Okay. So this says that, well, this is not the correct definition because you need to unnormalize that, but just say that this is unnormalized. Okay. The thing is that with respect to some norm, and we will see what's the definition of this norm, but with some norm, pick the vector that maximizes this with respect to some norm. And the whole difference between steepest descent and gradient descent is the choice of this norm. Okay? So if I give you some example, nice. So imagine that, I don't know, this is the landscape of the optimization. Oh no, let's see. Okay, that's okay. Just imagine that this is the landscape of the optimization, sublevel sets, and the gradient at this point is this. So this is, even let's say, yep, this is the gradient of f. So the minus of the gradient is somewhere here, minus of gradient at point k, okay? Now, if we define norm to be L2 norm, you recall the definition of L2. So this is the L2 norm, this is L1 norm, right? So if we pick L2 norm, then it means that here we draw a circle. So this is the meaning of this d of x. Pick that one and choose a vector that maximizes that product, inner product of the gradient and v, which is going to be like this one. Okay, so essentially it means that the direction that we're going to pick is exactly minus gradient if we are talking about norm 2. But then what would happen if the norm is not norm 2, right? So what would happen, let's say, if the norm is norm 1. So norm 1, or let's say norm infinity. Then norm infinity is going to look like this. And just imagine that the minus of the gradient is like that. Then what is the best vector here within this bound? The best vector is actually this guy, right? So what does it mean? It means that gradient distance says minus gradient, take this one. A steepest distance says that take this one. So if you just change the norm. Now, if we go with the general norm, define norm as like this, so ellipsoid. So we have seen the shape of this guy. So this for different p, we can rotate this ellipsoid, make it more like a line or like a circle, and then of course rotate it with the choice of p. Okay. So the thing is that what would happen if we go with this norm, and then you can see that by definition d gonna look like that. But then geometrically, it means that if the optimization landscape is like this, if we pick the norm to be very similar to the optimization landscape, so if the norm is this, and if the gradient happens to be minus gradient is this. So let me just go even for this example. Well, I can just show that. So here, for instance, the minus gradient is here because the minus gradient is just norm 2 and then finding a vector within norm 2 that maximizes inner product of that vector and this guy, which is essentially this way. But then what would happen if I change the norm and then make it like this? Then what is the best vector here? The best vector here is actually this. So this is the d of k at this step. And then you can see that we can converge. So then we're going to end up to some point here, and then another norm, another one, and then, so we can just directly go to the optimal solution. So this is the meaning of a steepest descent here. So pretty fast. Now, so the way that we do this norm with this p is actually the meaning of that preconditioning things that we have discussed. The p will do that for us. And then you can see that if you go for Euclidean norm, so norm 2, then that p gonna be identity matrix. So we will end up to the usual minus gradients. Okay? So then we can see that the good norm, in general, is not very concrete, but good norm is some norm that is somehow consistent with the geometry of the optimization landscape. So, but then what's the problem? The problem is that beforehand you may not know the geometry of the landscape. That's a challenge. Okay. Theoretical convergence is very similar to gradient descent, but it works much better in practice. So the number of iterations that you need here, for instance, could be, say, 1,000, but the number of iteration of a steepest descent could be like 10. Okay. What is the problem, though, here? The problem is just finding this p. What should be p? If you know, if you're handed in the optimal, the best p, then that's just perfect, use that. But then if you're working with high dimensional data, there are some good p, but then the number of bad p's are much more than the number of good p's. That's the bad thing. So here, for example, if you pick p to be like this, so let me just use this part. So if you pick here p to be like that, then the optimal vector here gonna be like this. Then the gradient descent will say that, a steepest descent will say that. That's a pretty bad norm. So that is the main problem. So the choice of the norm. Okay. But if you have some information about the norm, so the geometry of the optimization problem, then use this. Okay. And this is a bridge to the Newton methods. Okay. Any questions so far about the steepest descent? Okay, cool. So on the Newton methods, let's just see the landscape of the optimization close to the optimal solution, just close to the optimal solution. So in the optimal solution, we know that the gradient vanishes. So f of x with this quadratic expression, so Taylor expansion of f of x is like this, okay? And the good thing is that this Hessian here, so what does it mean? It means that it's like quadratic function determined by this Hessian, right? So this is actually ellipsoid. So we don't know how this optimization problem behaves, the landscape of this optimization is in all the points, but we know that if it's close and close and closer to the optimal point, then it's gonna be quadratic. So essentially ellipsoid. Ellipsoid that is determined by this Hessian. So this is pretty good information, right? So what about using this? Any idea? Using that, I mean that if you go to the previous slide, we can define the norm like this and then run a steepest descent. So find the good direction by this. So P inverse of gradient. So P here in this case gonna be this vector here, actually minus of this vector. Okay, here we should have a minus here. I missed that. But then P gonna be this gradient. But what this Hessian? But what is the problem here? Can we do that? So you see the connection. So we started from gradient descent, saw the problem that we need to somehow precondition the optimization landscape. Then we ended up to a steepest descent. The problem with the steepest descent is that we don't know the geometry of the optimization to be able to precondition. Now we know close to the optimal solution that the geometry is like ellipsoid, and then we know how to determine that ellipsoid. So we can do that. The problem though is that we don't know optimal solution. So that's why that we cannot find this guy, okay? So what about just replacing this with xk? Very heuristic, okay? Then we're gonna end up to Newton methods. So essentially what it does, it says that I don't know the geometry, but I will assume that it looks like an ellipsoid, and that ellipsoid will be determined by the Hessian. And at every iteration, I'm gonna find that Hessian and then precondition the optimization landscape with the inverse of that Hessian. So this is the meaning of this equation. So essentially, it's like running a steepest descent on this norm. Okay, well, not that norm, Hessian of f evaluated at x of k, okay? Just to be clear, that's not the main idea, the way that Newton methods has been developed. So the Newton methods has been developed for some other things, but then this is the interpretation that you can have, that if you run Newton methods, then this is essentially what it does. So you can imagine that whenever we are closer to some point, so whenever we are sufficiently close, that sufficiently should be defined anyway, but then whenever we are sufficiently close to the optimal solution, then the optimization landscape gonna be really ellipsoid that will be determined by this. So now we can run a steepest descent that converges extremely fast. And this is actually the success behind Newton methods. Okay, so with Newton methods, we can show that we had almost the same, so this is about the convergence of the Newton methods. So we had almost the same thing with gradient descent, with a strongly convex, LS smoothness, all those sort of things. Here, instead of having this C smaller than some C this, now we have some C this guy to power 2. Okay, so the previous one called linear convergence, this one called geometric convergence. Okay. And then the number of iterations is some constant, and that constant is to make sure that we are sufficiently close to the optimal solution. Sufficient close doesn't mean that so close, it's just after some points. So the convergence, if you look at the figures of the convergence rate, it's gonna look something like that. Whereas for gradient descent is like this, okay? So here, these are the constant terms. We are converging to the optimal solution extremely poor. But after some point, and this extremely poor doesn't mean so many iterations, like 5, 6, 7 iterations. After that, we are in that double exponential regime, and then we can convert double exponential because we have log. And then we can converge after 2 or 3 iterations. That's it. If you want some more accuracy, say epsilon, you want to make it 10 times more accurate, it's just 1 more iteration or 2 more iteration, nothing that more. Okay, what is the problem? The problem is just expensive iterations. So every iteration you're gonna need to find this Hessian and then take the inverse of that Hessian. So if the dimension of the data is so huge, then this is okay, you can find that, it's still hard, but then finding the inverse of this is gonna be so complicated. So that's why that in large scale optimization, in some cases, not all, we are not using that, that approach, okay. Another very good property of this is affine invariance. So what does it mean? It means that if we change the coordinate by multiplying by some non-singular a, and if we want to run the gradient descent on that, then what would happen is that the gradient of that guy is a transpose the gradient of the previous one. So what does it mean? It means that you're running gradient descent. Let me see here. So you're running gradient descent here. You're finding some transformation of this, changing the coordinate, making this. Now the gradient descent cannot converge, essentially, in practice. So essentially, if you have gradient descent, if you have some linear transformation, change of the coordinate, then you can destroy the whole gradient descent thing. But then this is not happening for Newton methods. It's completely invariant to that transformation of the coordinate. So for any coordinate, say a y instead of x, you can go with any coordinate and just do the Newton methods on that new coordinate. And there is a very clear way how you can come back to your original coordinate. Very easy. Okay. Again, what's the problem? So this is about this preconditioning, all those sort of things. If you find the right coordinate, then just go with gradient descent. But usually it's very hard to find those coordinates, those p in the norm of the coordinates. I guess that I'm spending just 2 minutes on proximal method, which is the last part of this lecture. I don't have time for acceleration at all. Okay, so let me see. Smoothness implies this one. So this proximal method is generalizing everything that we have seen so far. Okay, so again, we have started with gradient descent, the steepest descent, Newton methods, and now proximal method, which generalizes everything. So assume that the function is smooth, and one of the inequalities that you're gonna prove is like this. Okay, so a geometric upper, a geometric upper bound, a quadratic upper bound on the function. That should be f of xk plus 1. Okay. You can write down the iteration of the gradient. This is very easy to write it down. You can write down the gradient, the iterations of the gradient descent, which we do have it here. This guy is exactly identical to this guy. So minimizing this quadratic upper bound. So if we know that the function is L smooth, then you can say that we have this upper bound. So this is the function. This is the function. And this is our xk. What we can do is that using L smoothness, we can say that this is the upper bound. Okay, so this is the right-hand side of that equation. Again, that should be f of xk plus 1. And then find the optimal point here. Call it xk plus 1. Actually, map it here. And then call it xk plus 1. And then this is f of xk plus 1. Okay? So this is the meaning of that. You can find this. So the upper bound. So you can say that that gradient descent will run a sequence of quadratic upper bound minimization, essentially. And the upper bound is found through a smoothness. Okay. Now what would happen, that's quite great, but then what would happen if instead of minimizing f or minimizing g, say, you want to minimize g plus some h, where g is convex differentiable is just fine. We know how to handle g, but then we don't know how to handle h because it might be non-differentiable. Where you will see that, for instance, one example is if you have norm 1 regularizer here, so a sparse regularizer like Lasso, or whatever that's not differentiable here, you can have that, plus some loss function. So this can be your non-differentiable, even non-smooth regularizer, and then that can be your very good objective function, well, loss function. Then how you handle that? So one may say that, just think about that. But then one very simple heuristic that's the basis of this projection method, proximal method, is just completely ignore h. Run this, but just plus h here. That's it. So don't do anything. Just go with upper bound of g using the smoothness and everything, and just add h here and then try to find this x here, okay, based on that. So if you do that, then you're going to end up to something called proximal mapping, which is, this is what I just said. So an upper bound of the function, this is exactly this upper bound, plus some h where we don't know how to handle. Okay? So this is called proximal mapping, and proximal method is just to solve this one. Okay, so you can recall that this is the gradient descent iterations, okay? And then with proximal mapping, you can map. So what is the good thing here? The good thing with this one is that for some functions, the good thing here is that for some functions, h could be very complicated, but the proximal operation of over h could be extremely simple. So in that case, you don't need to be worried about how h is complicated or whatever like that. Irrespective of that, this proximal, you can find that very easily in some cases, not all cases. And it just happens that for these cases, which we will see a lot in practice, this is exactly the case, okay? So you can just write it down. I just need to wrap it up. So you can just write everything down and then show that this iteration here, just plug in this guy here. And then you can show that xk is like this. So this is what I just said. So this is like quadratic upper bound plus h. And then this is exactly what the proximal method is doing. Then you can see that the gradient descent is exactly a proximal method with h of x equal to 0. The projected gradient descent, where you want to minimize some objective f with subject to some constraint, convex constraint, you can show that this is exactly a proximal method with this h, which is indicator function if x in that set or it's not in that set. So you can just run proximal method. It's fun to show that this is exactly the proximal operation of this guy over h, gonna be exactly that. With that, you will end up to the projected gradient descent iterations. And if you have some f plus that h in this form, then the good thing is that for this guy, the proximal operation is like that. So you can just go replace x with your famous gradient descent iterations and just run this for the proximal iterations. So working with this guy could be extremely complicated, but working with this guy is just very simple. What is this? This is essentially called soft thresholding. So it's like something like that. If something greater than that's line, that's line, that's line. So very easy to compute this guy, independent of the hardness of computing this guy and optimizing over that guy. So that's it. Thank you, everybody.